All right. So as I just mentioned, this is being recorded in MS Teams and will be available on BAI's YouTube channel at a later time if somebody else wishes to watch it at that time. Okay. So this presentation is about Scour critical bridges. And what we're going to do today, we're going to go through some definitions regarding Scour and Scour critical bridges. We're going to talk about the effects of Scour. We're going to look at what it means to be Scour critical, for a bridge to be Scour critical. We'll look at some procedures that have been put in place, legislation, new procedures that were put in place because of Scour. And we'll look at ways to protect bridges against Scour. So starting off with Scour, Scour is the removal of sediment from around the bridge abutments or piers. It's caused by water flowing, usually at a high velocity, creating scour holes and otherwise compromising the integrity of the structure. There are basically three types of scour that we'll be looking at. There's long-term degradation, contraction scour, and local scour. A local scour can be aggradation and degradation. They're basically two sides of the same coin. Aggradation and degradation are long-term stream bed elevation changes from natural or man-made causes that can affect the structure of the river where a bridge is located. I'm sorry, the stretch of a river where the bridge is located. Aggradation occurs when material from upstream is deposited in and around the bridge substructure. However, it's not considered when we evaluate the total scour for the bridge. Conversely, degradation occurs when the water removes sediment from around the bridge substructure without it being replenished from an upstream source. Aggradation and degradation can be accelerated by various types of development, river modifications such as upstream dam construction, dredging, straightening or narrowing of the river channel, or upstream development that results in increased runoff. Contraction scour is a general lowering of the stream bed at the bridge, and it may vary in depth depending on a number of factors. Contraction scour results from narrowing of the channel, which results in a faster flowing water and removal of material from the stream bed. It's different from long-term degradation in that contraction scour occurs in the vicinity of a constriction or a bridge. It may be cyclic or related to the passing of a flood. Some common causes of contraction scour include natural stream constriction, such as hard rock on the embankments. We saw that. I know Mark and Faisal are on here. They were up at a bridge on High Germany Road in Washington County and saw these, high, steep rock embankments. That's a natural constriction. Excessive number of piers in the waterway, which you can see in the right photo. I'm not sure. I believe that's the Hanover Street Bridge in Baltimore here. Heavy vegetation in the waterway or floodplain. Bridge approach embankments built in the floodplain, which constrict the waterway. So, for instance, if the road is built up approaching the bridge on each side and the surrounding area is lower, that might create a constriction and or a contraction scour. Perfect example of that's Dorsey Run Road. Right, the road is built up slightly around the surrounding area, and it creates a contraction scour or sets it up for a contraction scour. Formation of sediment deposits in the waterway along the inside radius of curved waterways, sandbars along embankments to constrict or reduce the available waterway opening. Good example of this is an Oxbow Lake. If you've ever seen pictures of Oxbow Lakes, this is basically what happens. Is the inside curve, it just keeps on scouring away and scouring away and scouring away until eventually it cuts, it makes its own shortcut and creates an Oxbow Lake. Contraction scour can also happen from ice formation or ice jams that temporarily reduce the water reopening and produce contraction, or flow under an ice sheet where the ice sheet actually contracts the flow. And then also debris buildup, reducing the waterway opening. Another recent example of this is one of the culverts that we're working on in working on in town of Kensington. When we went out there a year ago, there was about 50% of the opening was blocked with debris. Now it's at about 90%. So obviously that's a potential issue there. Local scour is similar, but it involves removing material from around the features in the waterway and is caused by an acceleration of flow resulting in vortices or eddies induced by obstructions. Okay, you can see what's going on in this left photo here. It's that's an example of local scour. So what's a scour critical bridge? Well, scour critical bridge is a bridge that's vulnerable to damage or failure due to scour. In other words, can scour cause the bridge to fail? If the answer is yes, then it's a scour critical bridge. If the answer is no, it's not. Pretty straightforward. As you can see in this image here, this is showing an example of how the surface, of the stream bed just erodes and erodes and erodes until there's nothing supporting or very little supporting the pier in the middle. One of the main ways that a bridge is damaged by scour is undermining. Okay, undermining is actually a type of local scour, and it's the scouring away the stream bed and supporting foundation material from beneath the piers and the abutments. Okay. Good example is settlement of the pier due to undermining. Okay, you can see here the pier, the one end of the pier here has become so undermined that it's actually settled by, I'm guessing that's about a foot, and the bearings are no longer supporting those beams. So this bridge is really in dangerous condition here. Another thing that happens is scouring around the piles, making them unsupported. So pile supported bridges can be vulnerable to scour from undermining. Now, for those non-structural engineers, piles are basically long, slender members that are used to transfer the load from the bridge to a stronger underlying material. They work because of the confining soil around them prevents them from buckling. But you can imagine what happens here if something like this happens. All of a sudden, that bridge is supported on all these very long, slender piles or long, slender columns now that have nothing there to protect them and keep them from buckling. So one of the things that we always need to make sure of is that this can't happen. So one of the key things that happened in 1987 was a high spring flood caused the bridge over Schoharie Creek in Upper New York to collapse. You had a large snow melt that was combined with rainfall totaling almost 6 inches, which produced an estimated 50-year flood. So the third pier from the west abutment collapsed, and then it was followed later by the second pier. So this was an important time because what ended up happening as a result is that underwater inspection requirements were added to the National Bridge Inspection Standards, and it's now required for any bridge that's has continuously submerged substructure units every 5 years or less. Just for your information, Maryland Transportation Authority requires underwater inspections, I think, no less than 4 years. And what they did was they changed it to align with the normal bridge inspection cycles, which are 2. SHA also adopted a Scour Critical Bridge program. Their office structure implemented a Scour Critical Bridge program in the early 1990s, and it's still in effect today. The program is intended to identify bridges with actual or potential scour problems, establish a process for addressing scour problems, and minimize safety hazards to the traveling public. You can see from this image on the right, lower right, it's Chapter 7 of the Manual for Hydrologic and Hydraulic Design. So it's actually, even though it's developed by the Office of Structures, this is actually under the H&H section. And it was really important for us to establish interdisciplinary scour teams. We now have collaboration between hydraulic, geotechnical, and structural engineers to determine the risk of scour for bridges. So your geotechnical engineers, they take borings, they tell us what kind of material is down there, and they ultimately give us information that we need as structural engineers to determine how deep we need to go with our piles or our foundations. The hydraulic engineers will do studies to determine how much scour can we expect based on the geotechnical information that's provided. And again, that will inform our design. Now, there's a lot of text here. I'm not going to go through all of it, but one of the things in the bridge inspection world that we have to do is we have to identify scour critical bridges. So under the program, the SHA program, there were several ratings. There's a rating of U, which is unknown foundations. There are any non-interstate bridges with unknown foundations. They were required to be recoded by November 2010. In other words, we needed to find out what was going on, what kind of foundations they had, and recode those. You had number 6, which is that a scour evaluation has not been performed with the interstate bridge or it's an interstate bridge with unknown foundations. And this was really meant to be a temporary code. And it was had to be eliminated before 2008. And then you have 3 or below, which are all scour critical bridges already. We already know that they're scour critical. And so we had to develop a scour plan of action with countermeasures to be installed by April 2010. So all of these things, they all were addressed about 15 years ago. And now, since April of 2011, we've got a new set of codes that no longer include code 6. And U is still there for some of them, but there are plans of action for monitoring those bridges and making sure that nothing happens. So what do we do to prevent scour? Scour countermeasures. There are lots of different types of scour countermeasures. I'm hitting the main ones, but there are a lot of other ways that we can prevent scour. The main ones that we're talking about today are things that we have to think about, I should say, in determining scour countermeasures, are the type of scour, whether it's local, whether it's contraction scour, whether it's long-term aggradation or degradation. The channel size. Are we dealing with a big channel or a small channel, especially considering the size of the bridge we're putting over it? Abutment locations, pier locations, soil conditions, channel morphology, the shape of the channel, the features in the channel, that kind of stuff, and vegetation in the channel. Probably the most common form of the most common form of scour countermeasure is armoring. There are a lot of different ways that we armor, but this is most common at bridges. Riprap is probably the most common form of armoring. Okay, there are several classes of riprap that SHA uses. There's class 1, which are up to 15-inch in diameter. It's usually not sufficient as a scour countermeasure. Class 2 is up to 24-inch, and class 3 is up to 34-inch. And again, that hydraulic analysis that's done, the geotechnical information, all of that goes into determining what kind of scour countermeasure we use. And you can see here, it looks like these stones are actually partly grouted. This is another form of riprap. Big problem with this is the fact that these stones are all round. And the fact is that when they're round, they don't interlock very well. So you can see what they're doing here. What's wrong with this is the fact that the stones are round. What's right about it is the fact that they're grouting them in place to make sure that they can't move. But generally speaking, all the riprap that we use in this area is typically very angular, like on the slide before, so that it interlocks and is less prone to being washed downstream by a heavy flood. We also see grout bags used quite a bit. Grout bags are a lot of times are used in underwater applications. You place them, and just the exposure to the water itself starts to harden them, and they become a very good scour countermeasure in many cases. Something I haven't seen in this area is something called a rock bag. Is there anybody here? I'm just curious. Anybody here used or seen rock bags in Maryland or anywhere else?
Yep. Yep. Rock bags, including sometimes we have designed Gabion wire maze also, Mike.
Yeah, you're a step ahead of me. The next one I have is
Oh,
gabions,
sorry for that.
right? So, but that's there's a difference there between the rock bags, which are these kind of flat bags of stone. They're not rigid the way gabions are. I found this very interesting, though. I mean, they actually are used quite a bit, but I've never seen them in Maryland. So I was just curious about that. In Maryland, we do see a lot of gabions, though. That's a very common thing. And we have gabion mattresses, we have gabion cages of all different sizes. I don't think I've ever seen one that's quite this extensive before, but we certainly do use gabions quite a bit in Maryland for scour countermeasures. Another form of armoring are Ajax. And there are a lot of different forms of these. They're not just these jack-shaped ones, but they have a lot of different concrete, interlocking concrete elements that they use. And you can see they're actually cabled together to help keep them in place. These are usually used in much larger bridges, and a lot of times with either tidal flows or just very large rivers where you can get some very severe flooding in place. Other types of scour measures that we see from time to time, there's upstream channel control, downstream channel control, drainage control, bridge modifications. We can do these kinds of things to help mitigate scour, um, either before the water or debris gets to the bridge or after it does. So upstream channel flow, it's site-specific analysis is usually required for this, but we can do things upstream of the bridge to try to slow things down or divert the water away from the structure itself. We can use weirs, we can use dikes, okay, vanes. I've seen vanes used quite a bit. Trying to think of where I've seen this. I've seen them used quite a bit. Vanes and barbs are similar. Vanes direct the water through themselves. Barbs actually just direct it away from the embankment. But there's a number of different opportunities here. And this usually requires some laboratory testing and numeric modeling. Um, and there's a lot of design that goes into these upstream structures. Spurs will redirect flow at the bend of the channel. Um, they'll halt channel migration if they're done right, and they'll orient the flow more optimally for the bridge opening. Other things that can be done upstream, you can remove vegetation and sloughed riverbank material. You can, in some cases, you can widen or shift the bridge, and that's most valuable when the abutment is already damaged or washed out. But that is something that can be done upstream. Downstream channel control. Well, this is after it's gotten through the bridge. But degradation progressing from downstream can often be caused by head cutting. So you can use check dams or low weirs can be effective. You can use sheet piling around abutments, and I'll actually show you another example of that later on. And you can also line the channel with riprap, which we've already seen before. I believe we did that. I'm trying to remember what the project was. It was before I came on to Brutus, but there is a project that we use frequently to show, our hydraulic analysis capabilities and our stream embankment improvement capabilities. and we'd use riprap lined all the way up and down the channel to protect against scour. Other scour countermeasures, drainage control, so allowing infiltration prior to reaching the body of water. So, for instance, riprap at an outfall, it can slow the flow of water into the stream or river. It can reduce the volume of water entering the system, and it also reduces sediment entering the system. As far as bridge modifications go, of course, we talked briefly about increasing the bridge span, widening the bridge, okay, moving the abutments farther away from the embankment. Unfortunately, this could be very costly, but in some cases, it's a necessity. You either let the bridge collapse or you change it. You can reduce the flow reduction at a bridge opening. It decreases scour effects. It's useful in approach. It's useful if the bridge opening constraints flow enough to cause upstream flooding. So we can allow more water to get through the bridge and reduce upstream flooding this way. It's also more valuable when a bridge abutment's already been compromised, of course. The one in this picture has already been compromised, so you're really not going to try to repair that. You're going to come back and you're going to do something new. And most likely what they'll do is they'll build a new abutment behind it. So I said I'd talk a little bit about another sheet piling prevention. So if you recall those undermined piers that were standing on this forest of what looked like toothpicks underneath them, this is the Hayden Bridge. The Hayden Bridge is Route 40, US 40, over the Susquehanna River up in Northeast Maryland. And it turned out the scour analysis showed that under a 500-year flood, the 39 feet of soil that surrounded these piles that support these piers would wash entirely away. Ironically, during this period where the analysis was being done, we had two back-to-back 500-year floods, and the soil did not wash away. Nevertheless, because the hydraulic model showed that soil washed away, and the structural model showed that those piles could not support the bridge if they were unsupported, we had to find a way to confine the soil around these piers. And so what we ended up doing, these photos came from McLean's website. McLean did the actual construction. But what we ended up doing on this project was we needed to put a cofferdam around the piles, and that would confine the soil. Next problem, sheet piling was not strong enough to stand up on its own if that soil washed away. So we had to come up with a new method for creating this cofferdam. And we looked at a number of different things, secant pile walls, and we looked at concrete sheeting and all kinds of stuff, and we couldn't find something that worked. And in this case, what we ended up doing was we ended up taking pipe piles, and we ended up welding sheet pile connections to them, the kind of fist and knuckle connections the sheet piles use. And so these are interlocking circular piles. The circular shape makes them much, much stronger and able to withstand that loading. And so what they did was they put these piles all the way around, created a cofferdam, they dewatered them, they mucked them out, did the substructural repairs that needed to be done, and they left them in place. So, this was a really unique and a really neat kind of project to have been involved with. But again, it illustrates the effects that scour can have if it's not addressed. So this was a lot faster than I anticipated it would go, but that's our presentation on scour critical bridges. I'm happy to take any questions that you might have. and see if we can answer them for you.
A very good presentation, Mike. It's very fruitful. I am just curious. In the earthquake-prone zone,
Yeah,
whatever we provide for the stream flow scour, the liquefaction scour comes into play
that's
because
a good
when
point.
the earthquake vibrates, groundwater comes up and
Yeah.
liquefies the soil. In that case, do you know what would be the best option to prevent the liquefaction scour of the bridge pier? I know in Japan and couple of places they hardly use grouting. Is there
Hmm.
any other measures in your mind?
Yeah, I mean, I fortunately in Maryland we don't have to deal with earthquake prone areas as much, but so I'll be honest, I'm not as familiar with the
Yeah.
ways that you
Yep.
would address it, but
Hmm.
I would think, something like we did at the Hayden Bridge.
Uh,
Um, at least the soil remains confined. So
yeah.
if you had liquefaction occurring around it, um, the soil inside, even if you had liquefaction occurring, it couldn't go anywhere because those piles, for instance, are embedded in the rock below.
Yep. Yep.
So unless the rock goes somewhere, the soil can't go anywhere, and so the bridge would remain standing. Um,
Exactly.
but that is a very good point. You have different countermeasures that you have to consider when you're dealing with earthquake prone areas. You know,
Thank you. Yeah. Thank you,
yeah,
Mike.
Yeah, Mike can
Mike, can,
answer since I worked on earthquake in Turkey. So if you want,
yeah.
I can answer what we did, our
Please
experience.
go right ahead.
Yeah. So when we were designing, abutments and piers with the earthquake zones, so we would, design the piles underneath the foundation. We would give the same horizontal forces, the vertical forces to the pile. We would design it as a pier, and we would, according to that, we will give all those moments and actual forces to the pile. So even if there is no soil, so that loading could be carried by those pile alone. At the end, it would be socketed to the soil at the very bottom. So that also would be determined by the geotech, so they can see like where can we go, what is the safe zone for the piles. So all the forces, horizontal and vertical forces from the earthquake, would be given to the piles, and that would be designed such as there is no soil confining those
Right.
piles.
So basically, they're designed as columns.
Exactly.
Yeah, yeah.
Thanks.
There you
Yeah.
go.
Thank you, Mohammed. That is another. Thank you for the explanation. That helps a lot.
Yeah, very good.
Thanks.
Any other questions?
Mike, this is Limashav. I have just to comment on, where the Susquehanna Bridge, you were saying that, hydraulic analysis indicated 39 feet of scour, but it
Yeah,
didn't happen.
yeah.
So thing is, basically, as a hydraulic engineer, whenever there is like you were talking about the contraction scour. So basically, when for 500-year flood or 100-year flood, the velocity is very high,
Yes,
with a lot of shear stress, a lot of forces, and basically it is going to have a lot of contraction score as well as the local score, which we discussed.
yes.
Uh, so what happens is, so it is possible. I'm not saying it could have happened. So it is possible that 39 feet, maybe 37 feet or 41 feet might have occurred, during the high velocity zone. But as the hydrograph descended, so basically the flow velocity got reduced. So whenever flow velocity got reduced, it means it is depositing the sediment. So basically there
Well,
was
it,
scour, and then afterward there was aggradation there. So it may
it's
have
interesting
already
that you
filled.
say that. That was actually one of the things that we considered. Of course, I wasn't involved in the actual hydraulic analysis, but
Right,
one of the things that we did talk about during this whole process was just that, the fact of resilting going on.
right,
And the problem was that they didn't have any way to tell if they were looking at new silt or old silt.
right,
There are things that they can put in place that will measure how much silt has washed away. Even if new silt is put back in place, what they have are um, probably the simplest way to think about it is like a donut on a pile, and this donut rests on the stream bottom. And when the soil underneath that washes away, that donut drops, and there's a gauge that measures how far it drops. So even if the silt comes back over top of it later on, you know how much silt has scoured away.
That's
And
right.
so they considered putting in some kind of measurement device for determining the amount of scour that was occurring. But in the end, they just decided, you know what, we're not going to risk it. We're going to assume that the model is correct and that this is what's going to happen or what can happen. And so they decided to reinforce the soil surrounding the piles. So
That's correct. At the same time, anything silt, whatever aggradation is occurring, so the soil is not that much compacted compared to the original
correct.
soil, which has been washed away. So basically,
That's
we cannot
correct.
just take the credit of aggradation there.
That's absolutely correct. You're right. When the silt comes downstream and is deposited back around these, features within the stream bed, yeah, it's clearly not as dense as the base material,
Correct.
and so it's subject to being washed out more easily. And so then the next storm can take it down even farther. So it's and I guess all that is to say, I'm sitting here, I'm looking at my screen, and I'm seeing lots of water resources engineers on this call, which is great. And but it's all to say that hydraulic modeling is an imperfect it's an imperfect science because
That's
we're
correct.
only as good as the information that we have to input it. So it relies heavily on geotechnical information. Well, one boring at one location, you might have one boring every 40 or 50 feet, which, there's a lot of information that we're having to kind of bridge the gap between these borings. So, it's we have to take it at face value and work with what's there. And so we want to prevent these bridges from getting scoured away. And so, on our side, on the structural side, when we do inspections, one of the things we're always looking at is, is part of the foundation visible? Has it been undermined at all? What's happening behind the abutment? Is there any piping going on where water is actually, going behind it? We see that quite a bit on culverts, where the water is actually working its way around the culvert instead of through it. So we're always on guard for those kinds of issues when we get into looking at bridges. We might not be experts on, the numbers of how it got that way, but we can certainly see what the likely cause is and how it may have occurred.
That's correct. I mean, you just said that very correctly that the hydraulic engineering, particularly in the Scour side, is very imperfect. So what happens is when the people who develop the formulas and they use laboratory results to put together some regression equation or some sort of deterministic equation to get the formula to estimate the scour, and there are so many parameters besides the D50 or
Yeah.
D84 or something like that. So they are always incorrect because they have not told that how we can scale it from the laboratory to the real world problem. So that's why they are imperfect. So in this case, what we do is basically we use sometimes different methodologies to give you the scour value. So one
Sure.
methodology might give you 2 feet of scour, which may not be true, but the other might give us 19 feet. So, but the whole purpose is basically to use the most critical one,
Sure.
irrespective, what we can do, or if if we feel like there is too much engineering judgment is needed there. If you like, it may be really over predicting scour. So basically, maybe from 3-4 methodologies, we can just average those values also.
Yeah. And correct me if I'm wrong, but also there's a difference in the way you approach scour for, say, large features in the riverbed versus smaller features in the riverbed. Is that
True. I
correct?
mean,
Yeah.
yeah, it is. And at the same time, it is sometimes it is single span bridge. We are more concerned about abutment scour. But at the same time, there is always possibility. You touched a little bit on the geomorphology of the stream. Some that natural channels are always shifting. Sometimes on the left side or right side. So basically, it is not necessary the abutment scour, the value which we have computed, is correct. Probably the contraction scour may or should be used at the where we have the abutment scour value. So basically, maybe it is higher than the abutment scour value. So we have to use a lot of engineering judgment there. So we cannot just assume one. So it is really state of the art. So I have another question. Suppose we have given you, some value of scour. We say Mahindra gave you the scour value of 18 feet for piers, and for the abutment he has given you 8 feet. So basically, considering those are the critical values and those are the highest value you got from various formulas. So how much deeper you would go, compared to our scour values given by the hydraulic engineers?
Most times what we try to do is if we're into using deep foundations, pile supported foundations, then we'll usually try to take that down to rock. Now, if the rock is just too deep, then we have to go deep enough that we're going to get a good solid bearing pressure, tip bearing on the piles. We do look at skin friction
Right.
with the piles. A lot of times it just depends on the agency. Some agencies want you to include it, but most times we ignore the skin friction because we consider that to be a very conservative way of looking at it. So we'll design for the pile tip bearing, and so that has more to do with the soil below it, and what the geotechnical information, the borings tell us about that soil. So we'll go down to a very, very firm underlayment of soil, underlayer of soil.
Even if the piles are founded on rock, we still have to check to be sure the pile is stable.
Yes.
With part of the material removed.
Correct. Sure. Yeah. So that goes back to that long, slender column thing that we were talking about. So, you mentioned, let's say the pier was going to scour by 18 feet. Well, we would have to look at it, assuming that 18 feet is scoured away, and make sure that those piles can remain unsupported for 18 feet of their length, and probably a little bit more just to be safe. So we have to make sure that they can stand on their own. Yeah.
Right.
And also the calculating the scour depth, the discharge plays a lot of role, right, Mike?
Yes, absolutely.
That's correct. Yeah.
Yeah.
Discharge and velocities, particularly the velocities give you,
Yeah.
on the shear stress.
Yeah. No, if there's one thing I remember from fluid mechanics, is that when the channel narrows, the speed gets higher.
That's right. That's the velocity. That's the force.
Right.
Yep.
So,
yeah, the discharge need to be maintained. Therefore, if the area is less cross section, then the velocity need to bump up.
Correct. Yeah, I didn't love fluid mechanics, but I do. That's always stuck with me.
Yeah, I like the example that you gave when the sediment deposition forms the delta and the cross section of the river goes narrow and
Yeah.
velocity goes up to maintain the discharge and its scour goes up.
Yes. Yeah. Are there any other questions? Okay. Well, hearing none, this will be available. As I said, it's being recorded. It will be available on BAI's YouTube channel for further viewing at a later time. If you have any other questions that I can answer, please feel free to reach out to me. Of course, we have Salim and Mahendra and their entire crew here to answer other scour-related questions as well. So we've got a really good team here to be able to look at these kinds of things. I see several people from the Highway Department, Pushkar and Shayak and Habib. Thank you for joining. We really appreciate it. And again, Any questions come up, please feel free to reach out to us.
Thank you, Mike.
Mike.
Thank you.
Thanks, Mike.
Thank you.
Thank you.
Thank you.